In this video, we're going to go over section 2.4 from our textbook, which goes over the absolute value function. So if you remember, the absolute value function is defined by this here. So for values of x that are greater than or equal to 0, we get x. And then for values of x that are less than 0, we get negative x. And so we'll use this concept to define the absolute value of an actual function, f of x. So if f of x is greater than or equal to 0, the absolute value of f of x will just be f of x. But if f of x is less than 0, then we have that the absolute value of f of x is minus f of x. So we'll look at this example here. This graph here is a graph of this function, y is equal to x minus 4 squared minus 3. And this is, if you remember, a parabola that is shifted 4 units to the right and 3 units down, just by this here. But if we were to take the absolute value of this function, so take the absolute value of the whole thing, we would get this graph on the right here. Now the reason being is because we're looking at the absolute value of our function. We can think of this as any f of x values that are negative here become positive. So for example, if we were to plug in x is equal to 4 into our equation here, we get 4 minus 4, which is 0 squared, which is just 0. And so our output value will just be minus 3. However, for this function here, if we were to plug in x is equal to 4 here, we would again get 0 squared, which is just 0, but we would get the absolute value of minus 3. And we know that the absolute value of minus 3 is positive 3. So this point that was originally here, which would be a minus 3 here, becomes a positive 3. And then we can see the same thing for all of these negative points, for all of these negative values of f of x here. The absolute value function makes them all positive here. All right. So let's look at solving absolute value functions. So we're going to have a few cases of this. And the first case we're going to see is when our function is equal to some point p. Okay, so with this case, what we have is two options pretty much. So if we have that the absolute value of a function is equal to p, this means our function is either equal to p or our function is equal to minus p. And there's two ways we can think about this. First, because clearly if we were to plug in positive p into our absolute value function, we just get positive p. But if we were to plug in minus p, we again get positive p. So this is why we have these two options, p and minus p here. But we can also look at this graphically. So we know for the absolute value function that we input p, so this at this point here, so x is equal to p, our output is also going to be p. And then we also know that if we were to plug in minus p for our x here, our output is going to be p here. So at these points here, these are our outputs, f of x. So we see that there are two areas where f of x is equal to this p, and it is at minus p and p. Alright, so let's look at an example of this case. We have the absolute value of 4x plus 3 is equal to 11. So in this case, we're going to set it up like how we just saw. We know that the absolute value of 11 is equal to 11, and the absolute value of minus 11 is equal to 11. So we're going to have our two cases, either 4x plus 3 is equal to positive 11, or it's equal to negative 11. Okay, and then we can just solve for x for both of these cases. So taking away 3 here, we'll get 4x is equal to 8. And then we'll divide by 4 on both sides. So x is equal to 8 over 4, which is equal to 2. Okay. We can also have, we take away 3 on both sides of this guy, 4x is equal to minus 14. And then solving for x by dividing by 4, we'll get minus 14 over 4. And this simplifies to minus 7 over 2. All right, so then this tells us our solution set is going to be negative 7 over 2 and 2. So these are the two x values that when we plug x into our absolute value function, we will get 11. All right, let's look at this next example here. Now this might look a little different from the last example we saw, but it is in fact the same. We just have to do one step to this function here before splitting it into our two cases. And that is, we can just take out a 3 from both sides. So we get 2x minus 1 is equal to 8 minus 3, so 5. And then we see that this function is in the same form that we saw before. We have the absolute value of some function is equal to some number. And so then splitting this into our two cases, we'll have 2x minus 1 is equal to 5, or 2x minus 1 is equal to minus 5. So again, we're just going to solve for x here. So we have 2x is equal to 6, and then this tells us that x is going to be equal to 3. And then doing the same thing here. So we get 2x is equal to minus 5 plus 1, so it's going to be minus 4. So then we get that x is equal to minus 2 over 4, which is minus 2. All right. And then in this case, our solution set's going to be negative 2 and 3. All right. So the next case we're going to look at is when we have an absolute value function is greater than or equal to some number. So again, what we'll do is we'll look at this graphically first. So if we input some value p here, our output f of x is going to be equal to p. And if we input some negative p here, our output value f of x is going to be right there. Remember, in this case, we're looking at when the absolute value of f of x is going to be greater than or equal to p. So this is our p value here, and these are all of our f of x outputs here. So that means f of x is going to be greater than p over here and over here, right? So all of these f of x values are greater than than p here. So then this tells us that when we want to find f of x greater than or equal to p, we're going to have to look at values greater than positive p and values less than negative p. So then this means we'll have either f of x is going to be greater than or equal to p, or f of x is going to be less than or equal to negative p. All right, and so if we also had a strict inequality, so if we just had the absolute value of f of x is greater than p, it'd be the same thing here. We just drop this or equals symbol. It would just be greater than or less than here. So we'll look at an example, which actually is just a strict inequality. So we have the absolute value of 3 minus 6x, and we want to figure out when it'll be greater than 12. What x values will make this greater than 12? So we have our two cases. We'll have either our function will be greater than 12, and then, or our function will be less than minus 12. And then, like I said, we have a strict inequality here, so these guys are strict inequalities. If we had this greater than or equal sign, then we would include that here. All right, so we can just solve for x. first thing we'll do is we're going to want a positive x value in the end. So I'm going to move this 6x over. So we'll get 3 is greater than 12 minus 6x. Subtracting a 12 on both sides. We have 3 minus 12, so that'll give us a negative 9. And that'll be greater than negative, this should be positive because we added the 6x to both sides, so this would be positive 6x. So negative 9 is greater than positive 6x. And then solving for x, we'll get negative 9 over 6 is greater than x. Simplifying this, we get negative 3 over 2 is greater than x. And then just writing this with our x value first, we'll have that x is going to be less than negative 3 over 2. All right, and then looking at our next case, we'll do the same thing. We'll add 6x to both sides. So we'll get 3 is going to be less than negative 12 plus 6x. And then we'll add this 12 on both sides. So we'll get 12 plus 3, so we'll have that 15 is going to be less than 6x. So this tells us that 15 over 6 is going to be less than x. We're going to divide by 6 on both sides to get x alone. And then we can simplify this a little further by dividing 15 and 6 by 3. So we'll get 5 over 2 is less than x. So we get that x is greater than 5 over 2. All right. Then in this case, our solution set is going to be the following. We're looking at, if we look back at this graph, we're looking at values less than minus p and greater than p here. We're looking at f of x values that are either greater than p or less than minus p. So there's kind of this gap in our solution set here. So writing our solution set in interval notation, we're going to look at all the values over here. So that'll be negative infinity up to this point here. And then we're going to union that with this point all the way up to positive infinity. And so that point we found, so it would be negative infinity up to negative 3/2, and then union 5/2 up to positive infinity. So all of the values in this interval make this true, and then all of the values in this interval also make this true. Okay, and then the next case we'll look at is when we have the absolute value of f of x is less than or equal to p. So again, if we have this point p here, then our f of x value is this at p. If we have minus p, then our f of x value is right here at the point p. Okay, and then we're looking at values of f of x that are less than or equal to p. And this is p here. And just like in the last example, we saw all of the values of f of x that are greater than p are going to be all of these guys. So all of the values of f of x that are less than p are going to be these guys in this region. So all of our output values that are less than p are here. And we find all of these values within this interval, from minus p to p. So all of the x values in this interval will produce f of x values that are less than p here. So this tells us in this case, if we're trying to find when f of x is less than or equal to p, we'll have that f of x is going to be in between minus p and p, just like we saw here. So we're looking at all x values in this interval here. So looking at this example, and here we have, I forgot to mention, this also holds for a strict inequality. So if this was just less than p, then our options would be f of x is in between minus p and p, but not equal to. So this would just be a strict inequality here, if that's what we had. In this case, we have that 5x plus 3 is going to be less than or equal to 7. So our function is going to be in between or equal to minus 7 and positive 7. All right. And remember, we have this double-sided inequality. We saw how to solve these a few videos ago. So we're just going to solve for x, and whatever we do to one part, we have to do to the remaining two parts. So I'll take away 3 from this guy, because again, we're solving for x, and so what I do to that part, I have to do to the other two remaining parts. So all the way on the left-hand side, we have negative 7 minus 3, so it'll be negative 10. And then we have 5x still here. And then on the right-hand side, we have 7 minus 3, so that'll be 4. So 5x is in between or equal to negative 10 and positive 4. And then solving for x, we'll divide by 5 here. And whatever we do to that part, we have to do to the other remaining parts. So we get negative 10 over 5. So that'll be negative 2. X will be greater than or equal to negative 2 and less than or equal to 4/5. So all of the x values in this interval. And so our solution set is going to be from and including negative 2 up to and including 4/5. So we have our brackets here. All right. And then the last thing I want to go over is a few special cases when we have these inequalities. The first one, we have the absolute value of x minus 2 is equal to negative 1. And so we kind of want to break down what's happening here. Remember, the absolute value of an expression is never going to be negative, right? No matter what we plug into our absolute value, we're going to get a positive answer. So this tells us that this equation has no solution. And to write this formally, our solution set would be the empty set. Similarly, if we're looking at part B here, we have that the absolute value of x minus 2 is less than negative 1. Well, using the same logic that we just saw, remember the absolute value is never going to give us a negative number, and so this will never be less than negative 1. So this tells us, so we know the absolute value of an expression will never be less than negative 1, so our solution set is going to be the empty set. Okay. And then lastly, we want to look at the absolute value of x minus 2 when it's going to be greater than negative 1. And in this case, remember our absolute value function always provides us numbers that are going to be greater than or equal to 0. So whatever we have in here, it'll always be greater than negative 1. So this tells us the solution set is going to be all real numbers because the absolute value of an expression will always be greater than negative 1. Okay, so we can just use our logical reasoning of the absolute value function to answer inequalities like these guys here. Alright, so that'll be it for this video.